All right, now that we've established why you should care about the specific solutions, let's get back to the actual operation. I have two additional examples that I want to go over, but let's just not forget the general method for this. Step 1, get your general solution. Step 2, use your known point to solve for C. Step 3, use that known value for C, substitute that back into the general solution in order to get your specific solution. Got your integral properties. If you got stuff added or subtracted from each other, you can distribute the integral. If you've got constants, you can move it outside the integral symbol. When you're done with that, you should have something that looks like one of these identities. And the identities allow you to get rid of the integral symbol and the dx, which is what we're trying to do, at least for step 1 of this. All right, let's take a look at this problem. We're given acceleration as a function of time, a known time and velocity, as well as a known time and position. This is a little unusual, and it's asked us to find the specific solution for x as a function of t. Now, x is position, and we're given acceleration. Now, let's look at the formulas we got that I just went over when I was talking about kinematics in the previous video. We know that if we integrate acceleration, that gives us velocity, and we can do the integral to get the general solution, and then we can also apply this known value of velocity, v0 equals 0. In other words, we start at rest, and then this will give us the specific solution for velocity as a function of time. But that's not what the question actually asked for. The question asked for position as a function of time. So this is only going to be part A of our solution. Part B of our solution is going to be to take the integral of velocity, in other words, take the answer from part A, integrate that again. Integral of velocity with respect to time gives us position, and we do have a known position, namely x of 0 is equal to 3. Okay, so putting this stuff together, we can get x as a function of time. All right, so this is our game plan. First, integrate acceleration, get a specific solution that gives us velocity. Next, integrate velocity, find the specific solution that gives us position. All right, so let's go ahead and do this. We'll start with blue ink and then move on from there. Okay, part A. Velocity is the integral of acceleration with respect to time. So we got an A here, we got A equals stuff here, take this stuff in, put it in here, integral of -3 cosine of t dt. You can keep the parentheses or not, depending on whatever you want. All right, no plus or minus signs or no functions that are added or subtracted from each other, so we do not need this identity. However, we do need this identity because we got a constant there, that -3, that can be moved outside the integral symbol. All right, integral of cosine of t is sine. Okay, so we've gotten rid of the integral symbol and the dt. Next, we need to solve for c. Oh, and by the way, since we're doing two integrals, our plan is to do two integrals, we need to distinguish between the c we get for the first integral versus the c we get for the second integral, so we'll call this c1. All right. Next, apply our known value of velocity in order to get a specific solution for velocity as a function of time. v0 equals 0, that means that wherever we see a time, the stuff inside parentheses is our time, so when time is equal to 0, velocity is equal to 0. So wherever we see a time, we can put in 0, wherever we see a v, we can put in 0. Okay, remember that sine of 0 is 1. Do a little bit of math here. Okay, I made a mistake. Sine of 0 is not 1. Cosine of 0 is 0. Alright, so this should be, that should go away. There we go. Alright, so sine of 0 is 1. That means that, let's pick this up here. 0 is C1. Take that, substitute it back into here. And we get that velocity is equal to negative 3 times the sine of t. Alright, so that's our specific solution for velocity as a function of time. Part B. Take that, integrate it again in order to get position, or general solution for position. Okay, no functions added together, so we don't need this, but we do need this. We still got that negative 3, so we can move that outside of the integral sign. Okay, integral of sine is negative cosine. And don't forget the plus c, but now we're talking about c2 because we had c1 over here. Okay, two negative signs cancel each other out. Alright, so now we got our general solution. Let's plug our known value in order to get a specific solution. Or, sorry, in order to solve for c, and then we use the c to solve for, to formulate our specific solution. So, what this says is that wherever we see an x, we put in a 3. Wherever we see a t, we put in a 0. So 3 equals 3 times the cosine of 0 plus c2. Again, stuff inside the parentheses goes wherever you put a t. Stuff outside goes there. Okay, so cosine of 0 is 1, so we get 3 equals 3 times 1 plus c2. Well, this is easy. This means that c2 is equal to 0. Now, it is just a coincidence that c1 and c2 are equal to each other. This is not always the case, and it depends on these known points that you're given. Nevertheless, we are almost done. Let's switch to orange here. Take that, substitute it in there, and we get x equals 3 cosine of t plus c2, which is 0. So that is our specific solution for x as a function of time. Alright, last example problem, which is a little easier than the last one, or actually a lot easier. Give me a second. This one, the ink leaked through. Let me get a clean copy. Alright, looks like this copy is as clean as it's going to get. Alright, moving on. We're given acceleration and velocity, and we're asked to find a specific solution for velocity as a function of time. Now, we only need to do one integral in this case, and that is that the integral of acceleration with respect to time is equal to velocity. Okay, so this integral alone will take what we start with and give us what we need. The reason we had to do two integrals here is because we weren't asked for velocity in the last problem, we were asked for position. That's a little more complicated proposition. Nevertheless, start with this. And substitute in acceleration as a function of time. Factor out the constant. Apply the identity, e to the x dx is equal to the e to the x plus c. So e to the t dt is going to be 6 e to the t plus c. Alright, so that's our general solution. We now apply our known value. Wherever we see a v, we put in 16. Wherever we see a t, we put in 0. Don't forget, e to the 0 is not 0. E to the 0 is 1. Okay, do a little bit of algebra. And we get that c is equal to 10. Take this, substitute it back into here. And that is our specific solution for velocity as a function of time. All right, that's